Fourier Series for electrical engineers. Let's begin. In this video, I'm going to teach you what the Fourier Series is. I'm going to use Symmetry to calculate the coefficients of a Fourier Series in a simpler way. Then I'm going to apply the Fourier Series to circuits. And then I want to show you a genius way to use complex exponential Fourier Series, which will also lead to amplitude and phase spectra. But first, what is a Fourier Series? Well, you probably already know a series, like the Taylor series. You use the Taylor series to approximate another function using polynomials. A Fourier series works in the same way. We're going to approximate a repeating function using sinusoids. So now I'll show you an example of this. Here you can see a function which I've called f of x, which jumps up from 1 to -1 and so on forever. We're going to approximate this function using sinusoids, as I said before, which I'll call capital F of x. This is our first approximation using one sinusoid. If I increase this value of n, you can see that using more sinusoids, we can get a better approximation for the function that we had. And in a moment, I'm going to teach you exactly how to get the coefficients for the sinusoid. Another function which you can try this on, which I have g of x here. It goes up from -1 in a linear way to 1, and then repeats again. This can also be approximated using sinusoids. Here you can see how sinusoids add up to this function. In general, a repeating function f of x can be written as a sum of sine and cosine. And I've added this factor of 2 pi to make it repeat in nice intervals. Our goal now is to find these coefficients an and bn, because if you know those, then we know exactly which sines and which cosines add up to this function. So let's go over this term by term. a0 sine of 0 plus b0 cosine of 0. That's the first term. But sine of 0 is just 0. And cosine of 0 is 1, so the first term is b0. The next term is a1 sine of 2 pi x plus b1 cosine of 2 pi x. The following term, a2, b2, and so on. This b0 is kind of different from the rest, because it doesn't repeat, it's just constant. This b0 is called the dc part of this function. The other terms are called the ac part of the function. So our goal now is using a function f of x which repeats itself, find these coefficients an and bn. The trick is to multiply sine of 2 pi nx by sine of 2 pi mx. Here you can see the function sine of 2 pi mx from 0 to 1. I want you to notice a special thing about this function. Here from 0 to 0.5, this function is positive, and from 0.5 to 1 it's negative. If I increase this value of m, you'll still see the same pattern. So positive here, negative here, positive here, negative here. And it stays the same for every value of m, of course. Here you can see the function sine of 2 pi nx, where the same thing happens, of course. I want you to notice a very special thing. Here in this region, this sine of 2 pi mx and sine of 2 pi nx are both positive. So their product must also be positive. But then here, sine of 2 pi mx is negative, while this blue function is positive. So the product must be negative as well. But because these functions keep repeating themselves over and over again, this product from going from positive to negative must also keep repeating. So here you can see the product of these two functions. It starts with positive, then negative, and positive, negative, negative, positive, negative, positive. A very special property is that the area of the positive sides here and negative sides here always add up to 0. So the signed area of this function from 0 to 1 is 0. And it stays the same for every value of m and n. If I change these m, and if I change this n, this will always stay like that. Unless they're both the same function, and thus m equals n. And we're going to use this property to find these coefficients. So as we've seen, the trick is to multiply these functions, sine of 2 pi nx, sine of 2 pi mx. Then, what I said is that the integral from 0 to 1 dx must be 0 if m and n are different. However, if they're the same, this integral will turn out to be 1/2, no matter the value of n or m. Let's multiply both sides by 2 to get a 1 on the right hand side. This property of being 1 if n and m are the same and 0 if they're different has a special function. It's called a delta function. The subscript m, n means that if these two, m and n, are the same, it's 1. If they're different, it's 0. So there's really nothing special or scary about this. It's just a neater way to write it. Another property that we're going to use is that multiplying sine by cosine will always be 0. This is always the case. They're always out of sync. I'll leave the case of cosine of 2 pi nx multiplied by cosine of 2 pi mx as an exercise for you, but you'll find out that it's also 1/2 times the delta function. So now, given our Fourier series, fx can be broken up into sines and cosines, what we're going to do is multiply both sides by sine of 2 pi mx and then take the integral from 0 to 1. On the left hand side, so this fx, it'll just be simply this. On the right hand side, we'll get still a sum of a underscore n of the integral from 0 to 1 of these sines plus bn integral of these cosine times the sine. But as we just said, this guy is always 0, and this guy is a delta of n, m multiplied by an. So we get this, am divided by 2 delta m, n, and then it's still the sum. But if you take the sum, where n goes from 0 to infinity, eventually it will once be the same as m, and for every other value of n, it will be 0. So this is just am divided by 2. So what we have is that the integral from 0 to 1 of fx multiplied with sine of 2 pi mx is am divided by 2. Multiplying both sides by 2, we get that an equals 2 times the integral from 0 to 1 of sine of 2 pi nx times f of x. bn's happen to be the same, but I'll leave that as an exercise to you. But now, these are simply the formulas for the an and bn that we wanted before. So now it's just plugging in this f of x here, and then calculating this integral, and we'll get an. Then do the same for this integral, and you'll have bn. Let's try an example. Here you can see the function that we saw before. It jumps up from 1 to -1 and so on forever, and has a period of 1. What's the Fourier series of this function? Well, let's begin with an's. We just plug in this formula, and we get this. 2 times sine of 2 pi nx, because here, from 0 to 1/2, this function was 1, and it's -1, so minus here, from 1/2 to 1. Calculating these integrals, we get something that looks like this. Plugging in these 1/2s and 0s and 1, get this. Well, cosine of pi n, if you remember, cosine of pi, that was -1, cosine of 0, 1, 2 pi, 1, 3 pi, -1, so it's -1 and 1 repeating. It's -1 to the nth power. So we get something that looks like this. Simplifying this a bit, we get something like this. Simplifying it even more, this. an equals 2 divided by pi n multiplied by this. Now let's do bn. Simply plugging in the formula, we get this. And then we can solve these integrals. Sine of pi n will always be 0. Sine of 2 pi n is always 0 as well. So this whole term is just 0. All of the bn's are 0. So we get this for our coefficients. Let's now write the actual Fourier series. Well, as you remember, the Fourier series was this b0 times a1 sine of etc. This is 0, this 0, this 0. So just get a1 sine of 2 pi x plus a2 sine of 4 pi x and so on forever. Now let's calculate a1 and a2. This was our formula for an, so a1 must have been 4 divided by pi, a2 must have been 0, a3 4 divided by 3 pi, and a4 0, and so on. The formula that we got is that our function f of x, which jumps up from 1 to minus 1 forever, is a sum for every odd value of n, because 2 and 4 was 0, of 4 divided by pi n sine of 2 pi nx. If you don't like this n equals odd, which seems a bit weird, we can also start at n equals 0. We can replace the old value of n with 2n plus 1. So to calculate a Fourier series, just plug in these formulas and calculate these integrals, and then you just multiply these coefficients by the sinusoids. Our periods that we had were always 1. But what if you have a general period of t? Then you of course divide the sinusoids by t and make the integral go from 0 to t. If you go back in our derivation and calculate sine of 2 pi nx divided by t times sine of 2 pi mx divided by t, you actually find that is t divided by 2 times the delta function. So we have to divide by t here. So these formulas are the formulas for the an's and bn's with a general period of t. You might also see it written as this, where the integrals go from minus t divided by 2 to t divided by 2. And this is exactly the same thing. So now it's your turn. Calculate the Fourier series of this function, which goes down from minus 1 at minus 0.5, all the way up to 1 at 0.5, and then repeats forever. If you've done that, you should have gotten something like this. And with that, I think I've dealt with what a Fourier series is. But calculating them, as you might have noticed, is pretty annoying. So now we can use symmetry to make calculating them way easier. First, we need to define what we mean by symmetry. There are two types of symmetry. You have odd functions and even functions. Let's begin with odd functions first. I'm going to show you some functions which are all odd, and I want you to guess what they all have in common. First of all, a sinusoid is odd. Second of all, a line through the origin is odd as well. Third, this x cubed is odd as well. This function is odd. And finally, fifth, a hyperbola is odd as well. So, what do you all have in common? If we look at this x cubed, and look at these points specifically. For this x equals 1, it's exactly the same as x equals minus 1, but just multiplied by minus 1. Same thing for this x equals 1.5, x equals 2, and so on. So, when we have an odd function, if you only know half of the function, like this, you could predict the other half. You know that what is here at 2 seems to be 1.819, then minus 2, it must be minus 1.819, and so on. And at pi it's 0, at minus pi it must be 0 as well, because minus 0 is the same as 0. So what we've seen is that a function is odd if f of x is the same thing as minus f of minus x. So f2 is the same thing as minus f of minus 2, right? So if this was 8, for the x cubed example, then this would be minus 8 multiplied by minus, 8 equals 8. Now, what does this mean for a Fourier series? If a function is odd, and we know that sine is odd, just as we saw before, well, cosine isn't odd. So it'd be weird if we had cosines in our sum, even though it isn't odd. So if a function is odd, it must only have sinusoids in it, because a cosine would not make this function odd. So if a function is odd, Bn equals 0. Let's play the same game again. So our first function, f of 1, is simply the function y equals 3. This function is even. Next, this function is even. Third, this function is even as well. Fourth, this function is even, which is cosine. And finally, fifth, this function is also even. So what do you all have in common? Well, if you look here, if you look at some specific points, like these, then this function evaluated at 1 is 1.5, and its function evaluated at minus 1 is also 1.5. So as we can see, knowing just 1/2 of this function tells you enough to know the other half. So if this function is 1.974 at x equals 1.414, then minus 1.414, it must also be the same thing, 1.974. So from what we've seen, a function is even if f of x is the same thing as f of minus x. Cosine is even, but sine isn't. So in a Fourier series, it wouldn't make sense to add up sines, because then our original function wouldn't be even anymore. So if a function is even, in the Fourier series, an must equal 0. Let's do an example. Here you can see a half rectified cosine wave. What that means is, it's cosine of 2 pi x, but when cosine of 2 pi x would be negative right here, it's actually 0. Let's calculate the Fourier series of this function. Now it's an even function, so no an, only bn. So I have to calculate this to find bn. Minus 0.5 to 0.5 is actually a bit unnecessary, because as you can see, it's 0 here anyway. So we only have to go from minus 0.25 to 0.25. Plugging in our f of x, we get this. And if you notice, this area is exactly the same as this area. So we can also go from 0 to 0.2.5 and just multiply this area by 2. So what that gives us is something like this. Now I'll spare you the details, because you can calculate this yourself, but if you calculate this, you'd get something like this. Bn is this formula if n is not equal to 0, not equal to 1, and if it is, then Bn equals 1/2. Now it's your turn. Calculate the Fourier series of this function, and notice how you don't have to calculate 2 integrals, but just 1. If you've calculated this, you'd have gotten something like this for your answer. And with that, I think I'm done with symmetry. Now it's time to apply our Fourier series to circuits. As it turns out, there's nothing special about using Fourier series and applying them to circuits. It's literally just the same, but now our functions are sums of sinusoids. But this doesn't change anything. So let's do an example to show this. Here, we have a voltage source, a resistor, and a capacitor. We have to know the voltage on the capacitor as a function of time, where our voltage source has this as its voltage, which we calculated earlier as this sum. So now, what's the voltage on our capacitor? So using Kirchhoff's voltage law, Vs equals 5 ohms times the current plus V. as you might remember, in a capacitor, current is, in this case, 0.2 times dV dt, where V is the voltage that we want to calculate. So we have to solve V in this differential equation. And as you might know, when we have a differential equation, we can solve it using the Laplace transform, which will give us this. Simplifying it a bit, we get this. And now our capital V of S equals this. So we just have to take the inverse Laplace transform to get our original V of t. But first, what is our capital V of S? Well, this Laplace transform of lowercase v of s. So lowercase v of s was this without the Laplace transform. So when we take the Laplace transform of it, we have this. Now calculating the Laplace transform of sine, or just looking it up, simplifying this a bit, we get this. Plugging this into our capital V, we get this. Now we have to take the inverse Laplace transform of this to get V of t that we wanted. Inverse Laplace transform of this is easy. So let's begin with this. We have to do partial fraction decomposition on this term. This fraction has to be broken up into b and an a. But because this term is of a second order degree, because it's s squared, not just an s, this is actually not possible. Instead, what we have to do is bs plus c. So the numerator is of first order. Multiplying out this fraction, so s plus 1 times bs plus c, and this times a, we get that 8 equals the top side of their multiplication, so the numerator, which is this. S squared times a plus b plus s times b plus c plus 4a pi squared n squared plus c equals 8. But the left-hand side doesn't have an s squared or an s, so a plus b must be 0, and b plus c must be 0 as well. And only the constants, these guys, must equal 8. So we get what I just said. A plus b equals 0 and b plus c equals 0, shows that a equals c. So we can simplify this guy to get this. Solving for a equals c equals this. Now b equals minus a. So we have a equals minus b equals c equals 8 divided by 4 pi squared n squared plus 1. So now just plug that in. V equals this, where you know these coefficients a, b, and c. Now take the inverse Laplace transform. Get something like this, which might look really messy, but as you can see, e to the minus t is just s plus 1. And also s plus 1 here, so that's also e to the minus t. And this s squared plus 4 pi squared n squared, this bs part turns to this cosine, and this c turns into sine. Of course, everything multiplied by u of t to show that it starts at t equals 0. So this is our v of t. Nothing special. We still use Kirchhoff's voltage law, still the inverse Laplace transform and Laplace transform. Nothing is special about this. It's just that the terms are uglier. The calculations are simply just more annoying. Nothing special about this. So now it's your turn. Calculate v of t on this inductor, where v of s is this, which you have calculated before, and turns out to be this function. If you've done so, you should have gotten something like this, where a, b, and c are these terms. And with that, I think we're done with applying them to circuits, which really isn't that special. But now comes the beautiful part, like this, the best part of this whole video. Complex exponential series. A complex exponential, e to the 2 pi n j x divided by t, where t is a period, n is just some number, and g is an imaginary unit. What I'm now saying with the complex exponential series is that any complex periodic function, not real as before, but just any complex, so also real, can be written as a sum of complex exponentials. So e to the something. C0 e to the 2 pi j 0 x divided by t. E to the 0 is just 1. So it's just fx equals c0. This c0 is called the dc part. After that, you have these terms, c minus 1 and c1 times these exponentials, c minus 2 is c2, and c minus 3 is c3, and so on. Every term other than c0 is called the AC part of this function. And I want to show you how these add together to create our function f of x. Okay, so here you can see a graph. And in a moment, a lot is going to happen on the screen. So let's take it one by one. This isn't an x-axis and this isn't a y-axis. This is the real axis and this is the imaginary axis. This dot here is the output of our function. So now, the output of our function is 1 plus I. Right now, our function is just real and it's just 2. Right now it's imaginary and it's 2j. If I click this button, it just resets to 0. As you can see, this function right now only has a DC component, which is what I'm moving right now. It's a DC part. So right now the DC part is 1 minus j. With this capital letter N, I can add exponentials. So right now there's 0, just the C0, the DC part. If I move this to 1, there's an added exponential. This A shows the time. So if I change the time, what you can see is that the output of a function is moving. At A equals about 2, it seems to be a bit less than 1. Okay, so 0.982 plus 0.19j. And it's moving, it's changing with time. So this red dot shows the output of our function. This blue line shows the previous values. If I click this B, you can show the path that's traced out by this function. So now this C1 is moving counterclockwise with a rate of 2 pi radians per second. Although I've slowed it down so you can actually see it better. Here you can see the real part of the Cn. So right now the real part is 1. If I change it to 2, it's 2 times as large. So now C1 is 2. If I change to 3, C1 is 3. Then we reset it back to 1. If now I add 2 exponentials, we get this. Now, it's the sum of the first one, C1, which is moving counterclockwise, and then you add another one, C minus 1, which adds this clockwise motion. Together, they perfectly add up to a real function. If I change this C1 and C minus 1 to 2, it just gets twice as large. And I can also make the Cn's equal to 1 plus j. Then it will be on this line. By adding more and more n's, we get more complicated shapes. So what we can mathematically do is represent any function using these exponentials and just changing the Cn's. I can also change the Cn to maybe n. So it starts C1 would just be 1. But C2 would be 2. For higher values of n, we get more complicated shapes. And any shape can be written using exponentials. So then, how do you find these coefficients C0, C-1, C1, and so on? Well, we use the same trick as before. We multiply by e to the minus 2 pi n jx divided by t, and then take the integral from 0 to t. This f of x, since the sum of exponentials, will be an e to the 2 pi m jx divided by t. So it gets something like this, where Cm is the coefficient that was in the f of x. If n does not equal m, you get this, which simplified just to 0. If n and m were the same, you just get Cm multiplied by the period. But n equals m, so it's the same as Cn multiplied by the period. So this is just the period multiplied by Cn multiplied by the delta function. Solving for Cn, we get this. So with this formula, you can just calculate all of the Cn's. So let's do an example now. What are the coefficients Cn? Well, we can just plug in the formula. The period is 1, so it goes from 0 to 1. If we plug in f of x, we get this. Calculating these integrals, something like this. Plugging in the 1/2 and 0 and 1. And if n is odd, Cn equals minus 1 divided by pi nj. So we get this. N goes from minus infinity to infinity, not at 0. Of this, minus 1 of pi nj, e to the 2 pi njx. Here you can see the graph. So, here you see the output. If I start the timer, it's 1, then jumps to minus 1. And now it's your turn. Calculate the Fourier series of this function, but now using exponentials. If you've done so, you've gotten something like this. And with that, I think I'm done with complex exponential series. Now finally, we'll talk about amplitude and phase spectra. So why would you use amplitude and phase spectra now that you have the coefficients? They allow us to forget about the original function. So we don't have to think of the actual exponentials, just think of the amplitude and of the phase. The amplitude is the magnitude of our coefficients. The phase is, well, the phase. So our original Cn would be the magnitude with this phase. So let's calculate it for some examples. The magnitude of 1 over n is just 1 over n, but the phase is 0 degrees when it's positive, so if n is greater than 0, and it's 180 degrees, remember e to the j 180 degrees is minus 1, so it's 180 degrees when n is less than 0. So we get this. This is our amplitude, these are our phases. And here we plot them. This is our amplitude spectrum, and this is our phase spectrum. Just by looking at this, we can sort of figure out what our original function must be. So instead of looking at the actual coefficients, which might be complex, instead look at this, which has a clear picture of what is happening, although you might have to get used to it. Let's calculate the amplitude and phase spectra of cosine of pi n. When n is 0, this will be 1. When n is 1, this will be minus 1, and so on. So the magnitude is always 1, but the phase differs. If n is even, it will just be positive, so 0 degrees. When n is odd, it will be 180 degrees. So you get this. Plotting this, the amplitude spectrum is just 1, and the phase spectrum alternates from 0 to 180 degrees. Now let's do a hard example. 1 divided by 1 plus 4jn. Well, if you multiply the top and bottom by 1 minus 4jn, and then take the absolute value of that, you get this for Cn. And if you take arctangent of the imaginary part divided by the real part, you get arctangent of minus 4n for the phase. So The amplitude spectrum is this, and the phase spectrum is this. So now it's your turn. Calculate the amplitude and phase spectra of these functions. If you've done so, you should have gotten something like this. And this. And with that, I've dealt with everything I told you I'd deal with. Have a nice day.